Next I want to look at is valves, and talking check valve and isolating valves, basically not automatic control valves because they're a world unto themselves. Excuse me. In terms of isolating valves, options gate valve, and a gate valve base consists of a wedge that's moved perpendicular to this flow stream in order to allow or block flow. At one time, most gate valves utilized metal to metal seating, but nowadays with elastomers, which is a fancy word for basically synthetic rubber, has made the resilient gate valve the most popular. On larger valves, 18 and above, an integrally mounted bypass valve is sometimes utilized to ease the operation of the main valve by reducing differential pressure and or facilitating the controlled filling or draining of a line. If you're going to do that, then I would suggest the use of a globe valve, because globe valves are very good for throttling purposes, which basically, by the way, an automatic valve underneath the mechanism with the disc is basically a globe valve. Now, gate valves, and I apologize, there are two forms of gate actuation available. Non-rising stem, which means if the top one there, if you turn the handle which turns the shaft does not go up or down, but the wedge itself does, because there's a nut built into that assembly, so is and the shaft is threaded, so as you turn the handle, the thing will raise or lower. Okay? The other option is OS and Y, open shaft and yoke. And you can see there the shaft is basically connected to the valve, and the hand wheel up above has to be raised because of the action. As you turn the hand wheel, the whole shaft comes up or goes down. And it has one screaming advantage to get to later. You can take one look at it. Is it open or closed? With a gate valve, non-rising stem gate valve, you can't really tell where the valve is at, certainly from a distance, unless there's some indicator right up on it. But with an OS and Y, you take a look. The shaft is, which is why OS and Y are spec'd for fire pump services. Butterfly valves. Excuse me. A butterfly valve has a shaft-mounted disc that turns through 90 degrees, quarter turn, and they're referred to as quarter turn valves, to allow or block flow. Have a centrally mounted stem, the basic valves, with an elastomeric body. While better quality valves use a double offset shaft such that the disc only contacts the seat in a sweeping motion at the end of closing. Double offset valves have significantly less wear and can be metal seated. Now, you can see the one in blue is a basic valve, like is shown in the drawing there. Basically, it just turns and uses the rubber to the black stuff up there to do the elastomer, to do the sealing. Double offset has kind of a waping action to it. The seat at the bottom, it pulls off the disc. At the top, it to the right. At the top, it will pull off to the left when it's opened up. You can also get triple offset valves where the axis of the seat cone is offset from the shaft center line and the contact surfaces are angled. That's great if you're into requiring a metal seated valve. In waterworks, probably not worth the effort and cost. Butterfly valves can be mounted in an uneven flow path, will develop shaft torque if they're mounted as shown in the drawing to the left, where you've got an elbow and then you mount it with the shaft as is drawn there. The flow on that thing, because it's uneven, will create a torque on it. And have been cases where lever operated and that's happened, and all of a sudden it'll slam shut and you get water hammer. The proper way to do it is to have the shaft mounted as it shows on the right, so the flow is dividing on either side of it, and the fact the flow is unable that way, no problem at all. And another way to avoid disc slam, of course, use a gear operator. Now, globe valves, as I say, if you take a look at this, the basic action is you're raising a plug or disc, whatever, up and down on a seat. Flow comes down, under, and over, and that base is your basic hydraulics is used in an automatic control valve. The shaft, threaded shaft, is connected to the disc and is turned by a hand wheel, while a nut atop the yoke does not move. Note in this variant, there's different ways of doing it. You can have it so that it's attached and it will play, the hand wheel will move up or down, and there's others where it just turns and the shaft moves within it. But basically, globe valve, and we'll get into its advantages and disadvantages shortly. Ball or plug valves. A ball valve is basically a shaft-mounted round ball or cylindrical plug, and with a through port. A ball valve, I think we're all fairly familiar with. You turn it through, again, it's a quarter turn valve. Turn it through 90 degrees in order to allow or block flow. Plug valves, if it's a cylindrical plug, fine and dandy. That type of plug valve, straight up head plug valve, typically lubricated, and you don't see them very often in waterworks. Ball valves, by the way, can get in full port sizes, so the hole in the ball is roughly equal to the pipe size. Now, eccentric plug valves. It's basically a plug valve with only a portion of the plug remaining and held in position by the shaft ends. Mounting orientation is important. On a pump discharge line, the valve should be installed with the seat towards the pump, which means the flow arrow, which is pointed at the seat, is actually pointed opposite to what normal flow is when the pump is running. Why do we do that? These are pressure-seated valves, and when isolating a pump, discharge line pressure should tend to force the plug into the valve seat. If you see here the drawing, basically you've got here's your pump over to the right, and you see the flow at the bottom is right to left, but when the pump is stopped, the pressure is the way of the arrow. So we want the seat towards the pump. And another trick with these things, it's beneficial to have the shaft horizontal so that the plug actually acts like a little gate. And you can see here, if we're looking at it straight on, when it's open, the plug is at the top. As it closes, it comes down from the top and then finally closes off. The advantage there is that any garbage that collects in the bottom will not touch the plug, not be affected by the plug, or get to the shaft. It is the best way to do it. Now, with all these options for isolating valves, which ones are good? Little table. It shows those that you can use, like gate valves. For wastewater, butterfly valves, you can't, or globe valves. Through flow, and you can see good or fair. Throttleable. Gate valves should not be used for throttling. Butterfly valves aren't bad. Plug or eccentric valves are fair. Globe valves are excellent. Quarter turn actuation, in other words, turns 90 degrees, that's it. That has advantages when you come to remote actuators. Gate no, butterfly yes, and you can just follow the chart down. So use that as a guide as to which valve type I should be using. Check valves. Excuse me. Check valves are intended to permit flow in one direction but prevent flow in the opposite direction. And the two major things with check valves are head loss and closing speed. And closing speed affects water hammer. As the slower a check valve closes, the more reverse flow will be established before the valve is seated. I'm hesitating slightly because you can get dash pots and everything else for these things. Not a big fan, not terribly effective. Now for water, wastewater, swing check. The classic check valve is a swing check. You've got a disc suspended on a pin, hinge pin, and the disc is often keyed or pinned to that shaft, which can extend out to the side through a gland, packing, whatever. And on the outside, a lever again can be keyed or pinned to the shaft. This weight can be a weight to assist for closing, or a spring does the same thing to adjust the closing force. And there's pictures of them. There's basically the internal of a check valve, but you can have OL and W, outside lever and weight, or a spring, outside lever and spring. The issue is that, basically speaking, If you look at the check valve on the left, that long travel usually will permit flow, some reverse flow to occur before the valve actually seats. Then it seats, bang, and you get water hammer because of the sudden closing. What you're trying to do with the weights is to get it to close before you get much reversal. And the external lever weight or spring, you can see whether the valve is open or not simply by the position of the lever. You also can use it for pump back flushing, which I'm suggesting you don't. We'll get into that in a minute. Now, ball check valves. They're very simple, clog resistant, but again permit significant reverse flow before they close. So they're not very good for water hammer, and they're not easy. You can't tell which, if it's flowing or not, and back flushing is impossible. Flapper check. The flapper check is like a swing check, but much improved. The disc is rubber encapsulated, and a flexible flap serves as the hinge. Because the disc, the valve seat is at 45 degrees, as is the disc when closed, disc travel is much shorter, and reverse flow is minimized. Another thing you can do is arrange to have a proximity switch with a target in the valve, such in a relay, such that disc opening verification is possible, even though you can't directly see it. You can do it with a proximity switch. And a backflow option, if you can see on the right-hand side, allows back flushing of a pump in a safe and controlled manner. What I'm talking about is one of the tricks. If you have a sewage pump and the sewage pump gets clogged, one of the things that helps is to back flush it, and that can be done with a swing check. And how I've seen it done, how they do it is actually start the pump up, and even though it's clogged, it will develop some pressure and it'll open the check valve a little bit. At which point you go over, grab the lever, and force the check valve all the way open. At that point, you turn the pump off. And when you turn the pump off, of course, the pressure in the discharge will immediately backflow through the pump, cleaning it out and turbining it. Then you go over and turn the pump on, and there's a wonk because you're reversing the motor and the pump, and now you've got pressure. Now you can let go of the lever. What's wrong with this picture? Oddly enough, and this became an issue at one time and some research was done, oddly enough, the motor is not the problem. The motor can only develop locked rotor torque and locked rotor inrush. So although it may take a little longer than normal startup, it won't be the amperage, and the amperage will not be any higher than it would, and the torque any higher than what it normally is when you start the pump. So they really aren't a problem with the coupling or the motor. What is a problem is the poor guy standing there holding this lever open while the flow is going backwards. The problem there, if he leans forward a little bit and that thing catches, that lever will snap, and if he's holding on tight, it'll snap him into the wall or whatever. So under OSHA, Occupational Safety and Health Hazard Association, whatever, you can't do it. With a backflow device on a flapper check, you can. You simply go over, you screw that device in, as you can see, and having done so, the valve will open a bit and you can back flush the pump. Note that wastewater check valves should not be installed vertically if you can avoid it. In combined sewer applications particularly, you can get debris, and that debris can get in behind the valve and prevent it from opening properly. Now let's look at valves that are only suitable for water. Nun-slam. Nun-slam is again a poppet check, again a round seat, round disc, designed to minimize reverse flow as much as possible because it has short travel of the disc and a significant closing spring. And again, like we talked with automatic valves, the travel only needs to be a quarter of the seat diameter. And that's because, and I get a little drawing down here showing what happens. The area of a circle is pi. You can follow the formula, and you can see that d divided by 4 will effectively give you the same area as you have with the port itself. Okay, and there's the equation. The problem is that they have significant head loss, and valve position cannot be readily identified. You can get wafer versions of non-slam valves, but I would avoid them. Their head loss is even worse. It's just not the way to go. An interesting valve is dual disc, where basically it's two. The disc is split into two, so you actually have two halves on a common hinge pin, and there's a hairpin spring. See where it says spring on the drawing, that basically tries to force the two of them closed. They have very little movement when a pump shuts off, so they're pretty good at preventing or minimizing water hammer. And there's a stop pin behind them so the disc can't flop to either side more than they should. And as I say, with the short travel and spring assist, reverse flow minimal, the discs are easily open, so beware vertical downflow applications. And head loss is not bad with these. I will mention a couple of things. Number one, valve position not readily detected. If you do have a vertical downflow application and no other choice, had an application once where exactly that was it was a 14-inch line and out of a pump station, and about the only choice was to have downflow using a dual disc. The problem is that, as I say, the downflow, the weight of them, they tend to hold the disc open. Factory did a special, put in a special heavy-duty spring that would hold it closed. Worked, no problems at all. Now, like a butterfly valve, again, how you mount these things is important. You should not mount them so the shafts are as you see in the drawing on the left. What will happen is the uneven flow will cause the disc to flutter, and I've seen it, and it'll sit there and make noise. And the solution is basically to have it so the shaft is like it would be the butterfly valve, done so that the flow splits on either side of it. Another interesting check valve is a tilting disc, which should be considered a premium. The way to do it with water if you can. They have a disc mounted slightly above the halfway point, such that the disc closing force is largely balanced out. Seat is also angled to reduce travel. While not cheap, they have very low head loss, reduced water hammer, and can be provided with both visual position indicators, switch, whatever, by having that shaft extended out to the side and those options chosen. Now here again is a little chart showing what can be used with waste starter, what can't. Back fleshing, you can do it with a flapper check, you can do it with a swing check, but you shouldn't. Indication, those that tell you whether they're open or not. Head loss, and here the smaller the number, the better, the higher the number, the head loss. You notice the nun slam, and the other right next to that is water hammer, resistance to water hammer. And as you can see, the nun slam are very resistant to water hammer, probably the best of the bunch, but man, if they got head loss. The tilting disc is very good. Head loss is very low, and water hammer is not bad at all, and you can pick your way through that chart as you want. And I've got a note about the fact that you can play games. If you can verify indication and have a switch involved, you can put a timer in such that if a pump starts and a check valve doesn't open within a set period of time after the pump starts, you fire off an alarm and turn off the pump. Or same thing on after the time is expired, if it doesn't close, okay, when it should. And sort of a last note on check valves, duckbill check valves. Low head applications, elastomeric duckbill check valves, developed in '84 thanks to the EPA, better choice. Again, what is it, red valve? Tideflex is a known name, but they have competitors as well. It is not suitable for higher head application. Works good with drainage pumps or relatively low head gravity. You can get them in chambers and everything else, but for higher application, closed pipe, I wouldn't. They're just not comfortable with that, and I'm not either. Air release valves. There are three types of air release valves. The first one is automatic air release valve, intended to release air under pressure. Has a float with a lever mechanism that controls a small needle valve into a seat. They can release air under significant pressure. Some can release, and believe it or not, even in excess of 500 psi. but they don't let much air out. They let it out very slowly, good for getting stuff that accumulates, and they won't open under vacuum, which leads us to our next option, which is an air vacuum valve, basically effectively a ball floating inside the chamber going up against a rubber stop. It can fill a pipeline very quickly, let air out very fast because of decent size opening, and it can release or play vacuum breaker. If there's a suction, the ball is simply pulled away from the seat and air is sucked in. What they can't do is release air under pressure. There's just no way. Now, what's the third option? Oh, by the way, in a quick variation on air vacuum is a pump service air valve, as it's called, which is really nothing but an air vacuum valve with an adjustable throttled air discharge. So if you've got a vertical turbine pump and you want to get controlled air release out of the thing, you can throttle that air release so that the thing starts, air comes out until finally liquid comes on, the ball closes the valve off, great, and that air release is spring loaded, so if you do vacuum, if you turn the pump off, it will allow air to go back down. Have used them. The right kind of application, you want the water supply level has to be below the discharge, but if it's not too exotic, they work fairly well. Combination, this is the third combination. You have air release and air vacuum, and you can get a combination air release which has the features of both. It can release air under pressure and is also capable of releasing relatively large volumes of air when you're filling a line and opening under vacuum. Now, large ones like shown on the right, virtually what they're doing is taking a large air vacuum and off a fitting on the side, adding an automatic air release to it. In smaller sizes, you can, like the one shown on the left, you can get combinations that combine the features of both. Appreciate that air venting is typically less of a problem when you have sufficient pump inlet pressure, like boosters, because air will compress, and it's the volume of air that causes problem. Higher pressures reduce the volume of any air within a pump. Basically, air being compressible. If you have high pressures, any entrained air is usually not a problem because the volume of the air is actually got quite small because of the high pressure. So for what that's worth. Anyway, there's an introduction to selecting the valves that you need, and I do again hope that you have enjoyed this.